The fourth threshold of big history is the story of planet Earth, the making of planet Earth. Earth began forming 4.5672 billion years ago. And by 4.55 billion years ago, Earth was at almost the 12,742 kilometers in diameter that it is today. It's this roughly 12 million year story that's going to call our attention in this video. As we've seen, the solar system began, as all solar systems do, within a cloud of gas and dust. Many stars are born within this larger nebula of gas and dust, and our sun was just one of them. It's the sun that concerns us, so we'll move into a small sliver of the nebula, where what we can think of as a local molecular cloud of gas and dust containing many molecules and 12 minerals is spinning. In this small region, a disturbance has recently occurred, concentrating matter sufficiently to induce a gravitational collapse. Once the gravitational collapse of the cloud is underway, a central region formed. That region would eventually become our star. But first, what brought about that disturbance that induced the gravitational collapse to begin with? We don't know for sure, yet, but a likely candidate is a supernova explosion, which would not only create our star, but it would send shockwaves through a much larger portion of the massive nebula and initiate the creation of many stars. However this disturbance was actually induced for our sun, once it was set off, gravity alone took care of the rest. The gas cloud, which was slowly spinning, had more and more matter fall into the denser central region. As the matter fell in, the cloud began to spin faster and faster, just as a spinning figure skater spins faster and faster as they pull their arms and or legs in towards their center of mass. As the central massive bulge of matter spun faster and faster, it distributed the more wispy gas and dust cloud that was falling into the central bulge into a disk of gas and dust that was spinning around the central bulge, with some matter from that surrounding disk falling into the center for quite some time to go. As the matter collapses in the central bulge, our sun entered its so-called T-Tauri phase. This T-Tauri phase is prior to our sun turning on through nuclear fusion, but it happens when it's gravitationally collapsing. When the gravitational collapse occurs and a hollow is created in the larger nebula, a lot of radiation is released. The gravitational collapse itself causes the production of radiation as high energy as X-rays. And this radiation has two important effects. First, it sends out strong winds that clear out the region around the fetal sun of most of the light and gaseous elements up to a distance of around 500 million miles out, the limits of what would come to be the rocky parts of our solar system. And that's crucial for the making of our planet and the other rocky planets, and for the concentration of lighter elements that make up the huge outer four gassy planets. The radiation from this T-Tauri sun had a second important effect, however. It melted a lot of the bits of dust that were in the swirling disk around it, and those melted bits stuck to one another and formed little droplets of molten rock, which promptly froze out into chondrules. Frozen meaning, in this case, becoming solid from being liquid. They became little droplets of frozen out rock. For some chondrules, this process repeated itself, as pulses of radiation from the central star remelted them, and they went through numerous remeltings and refreezing outs. We now find ourselves in a very different solar system. From a cloud of gas and dust, we now have a concentrated bulge in the center that is well on its way to fusing atoms together in its core. Around this almost born star is a disk of a combination of mostly dust grains and chondrules within the first 500 million miles, and beyond that was mostly gas, although plenty of dust and perhaps even some chondrules could be found out there as well. But our focus is on the inner 500 million miles, where the chondrules and dust dominated. The now hard chondrules accumulated together with dust grains as well. These substances clung softly to one another through electrostatic forces. This stage of electrostatic coagulation formed concentrations of loosely attached chondrules and dust up to about a meter. But beyond that, electrostatic coagulation isn't strong enough to do much. How these objects got from the size of a meter to the size of a kilometer is something of a mystery, because gravity isn't strong enough yet to take over and collect the matter together to make planets. The leading theories picture turbulence-induced concentrations of matter where gravity can begin to collect matter because there is enough concentrated close enough to create a serious mass relative to the surrounding areas. But this is not a large rock, but rather an area of space where many coagulates are whirling around each other, and they're all whirling around the large bulge in the center, which at this point may likely have been a proper star. Our sun had been born, having become dense enough for the hydrogen to fuse into deuterium, which fused to become helium-3, which fused to become helium-4. Our sun is now emitting a large supply of radiation into surrounding space, and will not stop for about 10 billion years. But for our planet, the more interesting story is taking place around the sun, where billions of objects, a significant chunk of them kilometer-sized, spun around the sun in the center and entered the next stage of planetary development, accretion. With kilometer-sized objects, gravity takes over the show. These large, irregularly shaped objects imposed a significant pull on the smaller objects around them, which promptly fell inward and smashed into the larger body. Much more violent collisions between two large objects occurred as well. By the time some of these objects are 100 kilometers across, the amount of radiation being released by radioactive elements inside these growing bodies, along with the heat occurring due to the gravitational energy that's released as objects fall into each other, has reached something of a tipping point. Because the age of the atoms in the solar nebula were much younger when the planets were forming than they are now, there were a lot more atoms that were unstable and were decaying, emitting radiation which heated up whatever it came into contact with. Two of the more significant contributors to this cause were aluminum-26 and iodine-129, aluminum-26 decaying to magnesium-26 with a half-life of 730,000 years, and iodine-129 decaying to xenon-129 with a half-life of 16 million years. Another two contributors, although less significant, were iron-60, which decays to cobalt-60, which decays to nickel-60. The transition to cobalt-60 has a 2.6 million year half-life. The transition to nickel-60 has a mere 5-year half-life. And then manganese-53, which decays to chromium-53 with a 3.7 million year half-life. These and many others contributed to this radioactive decay heating up and beginning to melt the innards of these growing space rocks. By the time these objects reached 100 kilometers, their insides had started melting a little, and as they grew bigger and bigger, they melted further still. And this melting, along with the smashing that was occurring throughout this time, combined with the physical and chemical effects of the water inside these growing bodies, came together to make a whole new suite of minerals. Taking the amount of minerals in Earth's history from the 60 that could be found in the chondrites, or the chondrule-bearing meteorites, the meteorites that have those droplets that we spoke about, and these physical and chemical processes move us to the achondrites, the meteorites that have been so reworked that they no longer have chondrules, as all the chondrules have been destroyed. The planetesimals grew bigger and bigger to 500 kilometers in diameter and ever on. More and more massive they became until gravity began to force them into an increasingly circular shape. And inside them, and closer to their surfaces, radioactive decay, the heat of released gravitational energy from the smashing together, the water reacting with various minerals to transform them, and the differentiation of heavier objects falling downwards and lighter objects rising upward, brought about this new suite of minerals, bringing the total number of minerals in existence for our Earth and the solar system to 250. In this stage 2 of mineral evolution, 250 is over 4 times the 60 minerals that existed from stage 1, the chondrite meteorite stage. Differentiation of the planet proceeded via both physical and chemical means. First, the physical. All of matter is made up of atoms. The atoms, or atomic elements, all weigh different amounts. As Earth became increasingly molten, it melted into substances that do not join together with each other when melted, but rather stay apart from each other to an extent. They're like oil and water, forming their own melts within the larger melt, and then moving with that melt up or down depending on the density. Iron is the dominant atom in the melts that start falling down, and iron in the siderophilic or iron-loving melts, iron's the dominant atom in those melts, and iron at 26 protons beats out the oxygen, silicon, and magnesium, which are the main elements that would come to make up the mantle and crust that are the main elements in this other melt. Oxygen has 8 protons, silicon 14, and magnesium has 12, and because the iron mix is heavier, it falls to the center of Earth, and because the so-called rock-loving or lithophilic elements, those ones that find themselves in the oxygen, silicon, and magnesium melt, because they're lighter, they make their way towards the top. And I should mention that there are 2 other main groups of elements beyond these 2. They are the sulfur-loving or chalcophilic, sulfur being slightly heavier at atomic number of 16, so chalcophilic mixes tend to mostly congregate at the bottom of the mantle, above the iron core but below most of the lighter lithophiles. And lastly, there are the atmophiles, which across time would come to congregate in the atmosphere. This process of building up larger and larger planetesimals and protoplanets continued, with more and more protoplanets coming together until there was only one left in our orbit. Her name is Theia, named after the Titan goddess who birthed the moon. We're going to now leave Earth around 4.55 billion years ago. Earth is now very large, though not quite yet its current 12,742 kilometers in diameter, and it is red and black. Black in the areas where crust has been able to form and not be bombarded or radioactively melted back into the red molten planet that is spinning about its axis much faster than it is today. If you like this video, like it. If Big History is your thing, subscribe. And if you value my work, consider supporting it on LiberaPay.